Hello, I'm Kimura Fumie from University of Tsukuba, and I'm going to present my research titled Lively Free Viewpoint Video Generation using Video Textures. With the recent advancement in photography devices and networks, free viewpoint video is attracting attention for achieving advanced visual media. This video can reproduce views from arbitrary viewpoints by integrating multi-viewpoint images. The video shown on the right is the actual free viewpoint video generated from the multi-viewpoint images, which enables us to observe the subject from any viewpoint. However, one problem with conventional free viewpoint video is that it struggles to express a sense of liveliness because the subject is observed as a static object. First, let us compare the two figures. The left figure on the slide shows a static image, while the right figure shows a video of subtle movements, such as changes in facial expressions and breathing. In the right figure, we can get the impression that the presented object is alive through subtle movements. This suggests that it is possible to express a sense of liveliness through subtle movements. We consider the sense of liveliness is an important element for a better video experience. In this research, we focus on motion as a factor for expressing a sense of liveliness. The purpose of this research is to apply the expression of a sense of liveliness to free viewpoint video through subtle movements as shown in the previous slide. Specifically, we generate free viewpoint video of subtle movements by projective texture mapping in CG space. By projecting subtle movements onto a static 3D model, we can express changes such as facial expressions and breathing. In this research, we use video textures to represent subtle movements. However, simple repetition of same movements causes habituation in long-term observations, thus impairing a sense of liveliness. One solution is to create video textures from long-captured video, but this is not an easy task, considering the memory of the computer and other factors. The video textures method synthesizes long-time period videos that are not monotonously repetitive while maintaining video continuity by detecting similar frames in a short time period video and jumping to random frames. The red bar displayed in the lower part of the video shows the timeline of the captured video. By executing a backward jump to the previous frame in the timeline, we can confirm that the video is actually presented for a long time. In this research, we aim to improve the sense of liveliness by applying the technique of video textures. This is the overview of our method. First, multi-view video capturing, which gathers multiple views of the subject. Second, 3D shape reconstruction, which reconstructs the 3D shape of the subject from the one common frames of the captured video. Third, video texture generation, which makes video textures with subtle changes in movement from the captured video. Finally, projective texture mapping, which makes the video textures onto the reconstructed 3D model. In the first step, we will explain about multi-view video capturing. We conduct video capturing using a multi-viewpoint video capturing system. About 40 multi-view cameras are arranged in a circle around the target object. Each camera is connected to a camera control box that synchronizes the cameras. The height of each camera is set at the same level as the subject's eyes. Video capture is controlled remotely by a dedicated PC using the camera capable of high-resolution imaging. In the second step, we will explain 3D shape reconstruction. We reconstruct the 3D shape of the model using structure from motion. Structure from motion is a method to recover 3D shape from multi-view images of a subject. Specifically, the first step is feature points detection in the image and feature points matching between images from different cameras. Next, based on the matching results, the position and orientation of the camera is estimated from the geometric constraints. Finally, the 3D shape is reconstructed from the obtained position and orientation of the camera. The figure in the slide shows the actual reconstruction process. In the third step, we will explain about video textures generation. We generate video textures using the main camera images, which is the front view of the subject in the multi-view video. Firstly, the face area is detected in the main camera images. Then, we estimate multiple pairs of transition frames that have high similarity between frames. The method of determining transition frame pairs will be explained in detail in the next slide. The figure shows the case where 71st frame and 39th frame are estimated as a pair of transition frames. For each estimated pair of transition frame, we execute a backward jump with a certain probability. A backward jump is a move to a frame that goes back in a time series between transition frame pairs. In the figure, an example of a backward jump from 71st frame to the 39th frame is represented. By executing backward jumps, the variation in facial expressions will no longer be monotonous and repetitive. We explain method for determining transition frame pairs. The first step is to split the video frame for the input video. Then, for each frame, the similarity between frames is calculated using the sum of squares of the differences in pixel value. Next, multiple pairs of frames with high similarity are detected. Finally, among the calculated components with high similarity, the components that are more than a certain distance apart in time series are determined as the transition frame pairs. Finally, in the last step, we will explain about projective texture mapping. We map the video onto the reconstructed static 3D model by using projective texture mapping. The displayed figure is an observation of the projective texture mapping in the CG space from the overlook viewpoint. For the position and orientation of the virtual projector, we used the external parameters estimated by structure from motion. The figure shows the arrangement of the projectors using the parameters of the 8 cameras used for capturing the images. To present free viewpoint video, the virtual projector should be selected based on the observation viewpoint, which is the camera in the slide. In this research, we used a virtual projector with the shortest distance from the observation viewpoint. This is an example of free viewpoint video with subtle movements generated using our proposed method. The right figure of the slide shows the free viewpoint video presented from the virtual camera shown in the left figure. By paying attention to the facial expressions of the subject in the free viewpoint video. We can confirm that the subject is expressing subtle movements such as blinking and changes in facial orientation. We conducted subjective evaluation experiments to investigate the effectiveness of using video textures for expressing the sense of liveliness. Before the evaluation experiment, we hypothesized the following results. Hypothesis 1. A sense of liveliness is enhanced by mapping video textures. Hypothesis 2. A sense of liveliness is enhanced by the occurrence of jumps to transition frames. Next, we will explain the details of the experiment. We conducted our evaluation with 15 participants who observed videos that were virtually captured around a target object in 24 seconds. After observing the videos with each texture conditions, the participants rated the sense of liveliness on a 1 to 5 scale. 1. Absolutely no sense of liveliness. 2. Almost no sense of liveliness. 3. Neither. 4. Some sense of liveliness. 5. Strong sense of liveliness. This is the video shown to the participants. The videos are 3 types of 3D models, mapping different textures. The left figure shows a 3D model with static textures. The middle figure shows a 3D model with video textures without frame jumps. In other words, it shows a 3D model mapping monotonically repeating video textures. The right figure shows a 3D model with video textures with frame jumps. In other words, it shows a 3D model mapping video textures with randomness in motion. This is the result of the experiment. The figure shows the means, standard deviation, and t-test results for the response of the 15 participants. The t-test results shows a statistically significant difference between the sense of liveliness of static texture mapping and video texture mapping, with a 1% significant level. The result confirms that the sense of liveliness of the 3D model is enhanced by mapping video textures. Therefore, hypothesis 1 is proven. The t-test results also showed that there was no statistically significant difference between the sense of liveliness of video texture without frame jumps and video texture with frame jumps, even a 5% significance. This result confirms that the sense of liveliness of the 3D model is not enhanced by the occurrence of jumps to transition frames. Therefore, hypothesis 2 was rejected. The reason may be that the jump to the transition frame couldn't be noticed, because the video used in the evaluation experiment was only 24 seconds long. As a conclusion, we proposed a method to generate free viewpoint video that can express the sense of liveliness by using multi-view camera system in real space and projecting video textures onto a 3D model in CG space. As a result of our evaluation experiments, we confirmed that the use of video textures improves the sense of liveliness of 3D models. Thank you for listening.